Good morning, everyone. We're going to pick back up at the end of chapter 9 today with a couple problems, and then we'll begin chapter 10 afterwards. So we're in the last couple problems in the chapter 9 packet. We did this problem last time, but I thought this was a good point to kind of start from today, is to take a second look at this question where we're trying to figure out the bond order and magnetic property, meaning diamagnetic or paramagnetic, for the C2 2- ion. Now, the key would be we need to use the proper diagram for C2 and its ions, so that's the diagram on the left side. We use a diagram on the right side for O2, F2, neon 2, and any ions of those particular combinations of atoms. And then we have to think a little bit about what this diagram is showing us. We provide these diagrams on exams so you don't have to memorize the orbital order, but the way we are picturing this is these are two s orbitals for these second row atoms. These are their 2p orbitals. And so if I'm picturing a C- and a C- atom, the thought is think about how their orbitals are going to overlap with each other, starting from the atoms, or in this case, two C- ions. Carbon with a minus charge should have this number of electrons. How do I know that? Well, carbon generally should have 4 valence electrons, but then plus 1 for the negative charge. So I'm just filling 5 valence electrons into my diagram onto the atomic orbital side. So I'm going to do that on both sides here. Now, what really matters is what's in the middle. What's in the middle is our diagram for the actual ion. If you were to neglect writing anything in on the outside, that's probably okay. Like if you're on a test or something, you don't necessarily need to worry so much about how do we know what to fill in over here in the diagram. What we really need to know is what do we fill in over here, and then what do those orbitals look like? What are the names of the orbitals? What atomic orbitals lead to those orbitals? The atomic orbitals that lead to the orbitals are the indication shown. So the 2s bonding and anti-bonding orbitals shown up and down, bonding down, anti-bonding up. But then if we're looking at C2 2-, we could also just say, well, it's just 2 times 4 electrons plus 2 for the negative charge. So I just need to fill 10 electrons into the diagram in order of low energy to high energy. So I'm just filling in 2, 4, 6, 8, 10 electrons. So into the diagram, I'm just putting those 10 electrons in. So I can easily count the electrons in C2 2- without even thinking about C- and C-. But if you want to imagine what the diagram corresponds to, or how we get these orbitals and their relative up and downs, it's the thought of anytime we have an orbital where we get some bonding contribution, there should be an anti-bonding contribution. And then the picture of the orbitals, if we're trying to picture, well, what does this orbital look like? Well, picture the 2 nuclei of carbon. We have s electrons that are spinning around the nuclei. So the greatest density for that electron will be between the 2 nuclei. So that's a bonding orbital. So this would be the sigma 1s bonding, or it's not sigma 1s, sigma 2s bonding orbital, because it is comprised of the 2s atomic orbitals overlapping with each other. So it just looks kind of like an orbital where our s electrons are most probably located between the 2 nuclei. Another picture might just have this looking like this kind of a picture here. Greatest shading. The higher area of shading is just the greater probability of finding the electron. So the greatest probability of finding this electron is between the 2 nuclei. And so then the anti-bonding orbital is where the electrons are now, instead of meeting in the middle, they're now far away, so on the outside of the nuclei. So this orbital here would be the sigma 2s star. Star meaning anti-bonding, meaning it goes up in energy relative to its atomic orbital set. And then also that the electron density is not between the nuclei, but it's away from the nuclei. So the way this orbital would look is the greatest shading would be on the outside of the atom. So we have the greatest shading on the outside of the atom instead of in between the nuclei. And so if we try to make a bond, the anti-bonding orbital is breaking the bond. The net impact of a pair of electrons in a bonding versus an anti-bonding electron is lone pairs. So we tend to think of electrons that have been canceled out with anti-bonding electrons as just what we're writing as lone pairs within the Lewis structure. And then our net bonds, the actual bonds between the carbon atoms, are going to be net here in this molecule, because those are the actual bonding orbitals that aren't canceled out by some type of an anti-bonding pair of electrons. And then our next set would be the pi. Now, how do I know the pi 2p is next and then the sigma 2p? Well, a couple ways. One is that the pi set's the planar set, and there's 2 planar sets. And so if we're picturing the orbitals of carbon in these orbitals here, so one of the orbitals looks like this, one of the orbitals looks like this, and then the other orbital is sticking straight out of the page. So I'll neglect writing the second orbital sticking straight out of the page. And so then the other, and this is the nuclear center of that carbon atom. So the other carbon atom has its nucleus and then has this 2p orbital and this 2p orbital. And so which of those 2p orbitals aligns in the sigma in between the nucleus fashion? It's the one that's vertical like this. I don't know if that's vertical. I guess probably horizontal is a better word. So the horizontal, the 2p orbitals that are pointed straight at each other, they align their electrons in between the nuclei. That's the sigma bonding orbital, which is actually higher in the case of B2, C2, N2, and any ions of those atoms. That sigma 2p is higher in energy than the pi 2p set. The planar set is this bonding combination. Let me go in blue here. So these orbitals overlapping this way where you get a planar bond, that's our pi set. Now, how do I know that's the pi set? Well, one way is that it should be degenerate, meaning it should have another orbital that looks exactly the same. So the p orbital is sticking straight out of the page. So just picture two p orbitals that look very much the same. So then we get a planar orbital sticking straight out of our page. So we get two orbitals here that are the pi 2p set, and they kind of look like once they overlap. So imagine the p orbitals overlapping together. So the p orbitals start to look like planar bonds or nuclei, and then that's sticking straight out of the page. So hopefully you can see, there's better pictures, if you back up your notes a slide or two, there's better pictures of this than what I can sketch, but the key is that there's two types of orbitals that look just like that pi set. So our pi set is the one that's doubly degenerate, meaning there's two orbitals that are the same energy, and then the sigma set is the one that there's just one of. And then another thought could be, and sometimes people think, well, why don't we just take this orbital that's like on the plane of the page, and why don't we move it somewhere else? We can't really move orbitals. So orbitals are centered around the nucleus or spinning around the nuclei. So we can't really move the orbital, but we can allow the orbitals to overlap with each other. So we're just overlapping these orbitals to make that pi bond, and then we get two of the pi bonds. And then if we go down, we have to go up, so then we get our pi star with no electrons. So there's no electrons in the pi star 2p, and there's no electrons in the sigma star 2p. And so then if we're thinking bond order, because it says to calculate the bond order for C2, 2 minus, our bond order is just taking into account how many bonding electrons are there total on the molecule. So the bonding electrons are these two, and then those 6. So I have 8 bonding electrons. Then I'm going to subtract the anti-bonding electrons. So I have 2 anti-bonding electrons. And so I have 8 electron pairs that are trying, 8 total electrons that are trying to make bonds. I have 2 electrons that are trying to break the bonds that we're trying to make. So on average, I have 6 bonding electrons, and I need to cut those into pairs. So that's why we have the half here. And so that leads us to a bond order of 3 for a triple bond. And so if we were thinking that C2, 2 minus would probably look like this, that makes a lot of sense from a Lewis structure. So a Lewis structure that satisfies the octet role for both atoms. And then we look at the formal charges. The formal charge of each carbon should be 4, has 5. So we end up with what looks like here C2, 2 minus. So a pretty good comparison between a Lewis structure that makes sense from our Lewis structure rules from chapter 8. And then here we have a bonding model that shows it has a triple bond, a bond order of 3. And then we also then see that our bonding, like our sigma 2s, sigma star 2s results in those lone pairs on the atom. So we have a couple other questions that can use the other diagram. So this question here, what about the superoxide ion? So superoxide, if we remember from nomenclature, is where we have 2 oxygens bonded together with a net negative charge. Peroxide is where they have an overall charge of 2 minus. I think we looked at the diagram of O2, 2 minus previously. So let's take a look here at the superoxide ion. And so then, of course, we have to make sure to use the proper diagram for O2 because this is one of its ions. And so this is one of the cases where it might be kind of tricky to think, well, maybe one side is O, the other side is O minus to, on average, get the O2 minus in the middle. And this is where it doesn't really matter too much if you really know what to write for the O and the O minus. But I'm just kind of picturing oxygen should have its ordinary electron configuration. So an ordinary oxygen without a charge is a 2s2, 2p4. And so O with a minus charge should be 2s2, 2p5. So if I knew that, I can write these number of electrons in here. whether or not I write those in is not really super relevant, because what's relevant is, do I write in the middle what I get for O2 with a minus charge? And so O2 with a minus charge should have 2 times 6 electrons, but then plus 1 for the negative charge. So 13 electrons going into the Lewis structure and the MO diagram. So I'm counting up my valence count for the molecule just like I would my Lewis structure rule. And so then I'm just going to put 13 electrons in from low energy to high energy. So 2, 4, 6. Now for O2, you notice the only difference between these diagrams is this orbital here becomes more stable for O2, F2, neon 2, and ions of those combinations of atoms. And so that's the only difference. And we don't expect that you memorize that detail, so that's why we would provide these base diagrams. But that's 6 electrons so far, 8, 10. If we're doing O2 without the negative charge, we stop here and it has 2 unpaired electrons. And we get that key property that oxygen has unpaired electrons. That was one of the key details that we were missing from our other bonding models for O2. But then for O2 with a minus charge, we just add that 1 extra 13th electron. Then we now have just 1 unpaired electron. So still something we would call paramagnetic. And then I also being paramagnetic means having 1 or more unpaired electrons will allow this molecule to be drawn into a magnetic field. So we should be able to draw this particle into a magnetic field. The fact it has a charge allows us to do that too. So anything with a charge you can pull into a magnetic field anyways. But O2 doesn't have a charge, so molecular oxygen, if you take the electron away, you can draw that into a magnetic field as well, which is pretty interesting for a charge-neutral molecule. The previous example, the C22-, I asked to do the magnetic property and I forgot to write it in, but if you look back on the last slide, C22- had all of its electrons spin paired. If all the electrons are spin paired, then that's diamagnetic. So C22-, diamagnetic. Now, diamagnetic molecules generally are repelled by a magnetic field as opposed to being drawn into a magnetic field. So all electrons spin paired go diamagnetic. So I just forgot to answer that for the previous page. And so then what about the bond order for O2 with a negative charge? Our bond order would be a half. Then I just count my bonding electrons. So the most bonding electrons you can ever have is 8 within MO theory. So molecular orbital theory would say the most bonding electrons you can ever have is 8. And then we're always going to have these anti-bonding electrons in the way, minimally. So to get to 8 total bonding, we're going to at least have 2 anti-bonding electrons. So this means we're never going to get to a bond order of 4. The highest bond order we could ever get is 3 for any molecule in the second row of the periodic table. And we don't really go past the second row for these type of examples. But the most bonds you could get is a triple bond. So you're not going to get like any type of quadruple bonds between atoms according to MO theory. So we get 8 bonding electrons. Whoops, forgot to write the 8 in before switching color. Then let me circle in green my anti-bonding electrons. So I have a total of 5 anti-bonding electrons. So that gives me a fractional bond order, but that's okay. I get a bond order of 3/2. Now the bond order of 3/2 is kind of interesting because if I'm thinking of like what the Lewis structure might look like, if I was back in chapter 8, I probably would have thought, well, this is O2 2-. I know that's O2 2- because it's just like F2. F2 has 14 electrons. O2 with a 2- charge would have 14 electrons. If we were looking at O2 with a 2- charge, I'd have this extra electron here filling in my diagram for a bond order of just 1. So O2 2- is pretty straightforward in what it looks like. And if you remember the rule in chapter 8 for Lewis structures for like diatomics, or any case we had an odd count, was, well, take an electron away from either one of the atoms and see which one has the more appropriate formal charges. Well, it's the same atom in both spots. So if I have to take away the charge here to go to minus, and I have to remove an electron, then I can remove any of the electrons from either of the 2 atoms. I get the same Lewis structure. So this would be the Lewis structure from chapter 8 that I would get from Lewis structure theory for O2 2-. But now here in chapter 9, you kind of see a slightly different picture. Would be, well, what if we just had this. So that should be a total, let me count my electrons here and see. So I have 2, 4, 6, 8, 10, 12, 13. So it's kind of a peculiar looking diagram, but it kind of shows that what you have here is a fractional bond order. So you just have that extra electron now as a bonding electron instead of as a lone pair. So instead of thinking of a single bond here, we see, well, the molecular orbital theory says, well, what if you have like a fractional bond? So now each oxygen has 1, 2, if you think about each O in terms of the octet rule, now each O has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So each O is satisfying the octet rule, and we just therefore have this fractional bond order. So this is probably a better picture of what O2 minus looks like, where each O now has that charge you expect from chapter 4. So in chapter 4, remember we were looking at oxidation numbers. We would assign the oxidation number of each O to be minus a half, and O2 minus, the minus charge spread across the two O's. Here the actual formal charge in the two O's in this structure would be minus a half. So, because you're like taking like half of that one electron in between. Okay, so this is maybe perhaps a better picture of what O2 minus looks like, or O2 with a minus charge looks like here in chapter 9. So interesting, like that you can get a diagram for molecules that kind of shows you a bond order and kind of lets you maybe rethink a little bit about what a Lewis structure looks like. This also kind of comes back to like the O2, where like O2, we're almost like thinking how it has like these electrons here are just in two different orbitals, like one spin up in one orbital and the other electrons spin up in a different orbital. So when we're looking at O2, it's like the net pi bond was like there was one electron in two different pi bonds on average for O2. So we're getting a slightly different picture for O2 as well once we inspected its MO diagram. So the key details here within MO theory are, can you get the diagram correct? Can you understand what the orbitals are, what their symbols are? Like if we're symbolizing here, this should be the sigma 2s, sigma star 2s, because that's just the bonding and anti-bonding from the 2s. And then here's the sigma 2p, now lower in energy than the pi 2p. And then here's the pi star 2p. And then the orbital without any electrons is the sigma star 2p. Because we can give like an orbital configuration. The orbital configuration just kind of shows that we're putting the electrons in the proper order. So sigma 2s2, sigma star 2s2, sigma 2p 2, pi 2p 4, and then pi star 2p with 3. So this would be our configuration. So can we give configurations? Assign orbitals to get the configuration? Can we picture what orbitals might look like? Can we come up with bond orders? Can we think about how a Lewis structure connects? That might be a little bit of a deeper question of like, what does the Lewis structure look like for like a multiple choice exam? So I don't know if we'd really show you different Lewis structure representations that match an MO diagram, but that's also kind of an idea that you can get that's maybe a bit more advanced from the MO diagram, is then what does this thing look like at a higher level than maybe what the Lewis structure was showing us? Let's do one last example from MO theory. So this, I'm in my thing where the screen isn't updating again. All right, so yeah, so whoever controls the Wi-Fi router, I'll plug it and plug it back in. Wait like 30 seconds. All right, so what about a mixed diatomic molecule? Meaning, what if you had two different atoms like N and O? What does that diagram look like? And I just wanted to kind of show that this then refines maybe what we think the Lewis structure looks like. So the one example we'll look at here is NO. Is my pen not working? So NO, if you remember, we did this Lewis structure back in chapter 5, or in chapter 8, and we were wondering, does it look like this, or does it look like nitrogen, double bond to oxygen, where we kick the electron off of nitrogen? And so we got to these two Lewis structures by starting with like NO minus with 12 electrons and then kicking electron off for the 11 electron NO. So we have 5 plus 6 equals 11 total electrons. So we had an odd count. And if you recall, we were like, well, which atom is deficient of the octet? And we were looking at this as being the better Lewis structure because it put the 0 formal charges on both atoms. And this one was bad because it was negative and positive. It was like -1, +1. And so we're pretty much ruling out that that was probably not the best Lewis structure for NO. Well, let's see what MO theory says. MO theory, and if you go back to the one diagram where I had like B2, N2, O2, that is, you go from boron to carbon to nitrogen to oxygen, the orbitals are becoming lower in energy, and this is just due to the effective charge and the size decreasing with that same trend. So as you go left to right, you're going towards a smaller atom, towards a higher charge, and the effect that that has on the orbital set is it lowers their relative energy. So the orbital energies of our p orbitals are lower than our n p orbitals because oxygen is smaller. So this is just a consequence of n being bigger than oxygen, and the effective nuclear charge of oxygen being higher. So the effective charge of O goes up, reducing its size, etc. And then the other detail is that the more dominant kind of atom, or the atom that looks like O on that side, kind of keys in the diagram to look more like O, where the sigma 2p is lower in energy. But the key detail here is with this base diagram, kind of seeing, okay, it looks like the diagram for like O2, where the sigma 2p is lower than the pi 2p set. And then here we're just filling in our 11 electrons. So we just go in order of low energy. So 2, 4, pointer 6, 8, and then 10 spin pairing. And the 11th electron in the pi star 2p. And so we end up with the bond order calculation for this molecule. If we go to calculate the bond order, of course it's going to be fractional here because we have a total of 8 bonding electrons, and then minus the 3 anti-bonding electrons. So we get a bond order of 5/2, which then suggests too for this molecule, why don't we just kick an electron out of, like, why don't we just go with a fractional bond order here too, where we have an extra electron in the bonding pair, and then we just balance out the number of electrons on O and N to make sense. So it's 2, 4, 6, 8, 9. So we need one more electron in each atom. And so that should give oxygen 1, 2, 3, 4, 5, 6, 7, 8 total electrons around it in terms of its valence shell, and it gives nitrogen 8 as well. So a weird looking Lewis structure. I don't know how we would ever come up with this in chapter 8, but this is probably like a more consistent Lewis structure with NO. Now NO does have one unpaired electron, so NO would be paramagnetic. It would be drawn into a magnetic field due to having at least one unpaired electron. So we can predict that magnetic property. We probably would have predicted that from the Lewis structure here as well. So if we're thinking this Lewis structure, we probably think, okay, there's a lone pair there, so it's going to be drawn into a magnetic field. But then we also see this diagram here. Now, whichever one, it would be a bad question now to ask, what is the best Lewis structure of NO? Because both of those are good Lewis structures. The top one, like this one here, is the one that just follows our basic rules from chapter 8. And then this one here is just the one that's more consistent with MO theory. So two slightly different Lewis structures, but we can see a refinement and idea of what a molecule like this could look like by inspecting its molecular orbitals. Now, for larger molecules, the key would be, well, if you could understand the MO diagrams for molecules bigger than 2, then you'd be in good business for understanding a lot of properties of molecules. If you're interested in that sort of thing, probably like being a chemistry major, taking physical chemistry and learning about computational chemistry, quantum theory will allow you to see that development. So that's like way down the road for seeing what orbitals look like for larger molecules. You'll see some orbital analysis in OChem if you take 25, 10, and 20 on like benzene derivatives. So you'll see some bit of orbitals and MO diagrams for certain type molecules later on in a class like 25, 10, or 20. Okay, so with that, we're going to head into chapter 10, or I'm sorry, I just wanted to show this last slide. So this was the picture that we had started from, where this container here contains liquid oxygen, kind of like liquid nitrogen. It's liquid at room temperature that is boiling off. So you see the vapors coming off of the liquid. It's a liquid at really low temperatures. And if you pour that liquid between a magnet, you can see the O2 sticks between the magnet. So that's just the picture for seeing that O2 2- is being drawn into that magnetic field. And then it must mean that oxygen has unpaired electrons. And we saw through MO theory why oxygen had those unpaired electrons through its molecular orbital diagram. Okay, so just kind of circling back to the topic of probably why we introduced this theory is to better understand a really important molecule like O2 and then other molecules related to it in terms of those other diatomic molecules. Okay, so with that kind of like caps our chapters 6 through 9 that was on electron nuclear properties, then getting into bonding and 3D shapes of molecules. And so now the next 3 chapters are also kind of on a topic together, or even the next 4 chapters. So the first chapter will continue this kind of adventure, if you will, into Chem 1220, of gases to liquids to solids. That's where we'll end as solids here in Chem 1210. And then chapter 13 is back on solutions. So the kind of 4 key phases that you deal with in chemistry: gases chapter 10, liquids chapter 11, solids chapter 12, and then you'll see next semester, if you take 1220, or whenever you take 1220, if you do, you'll see we start with solutions in that chapter, or in that class. And so let's talk a little bit about here, an overview of the chapter. So we'll talk about characteristics of gases. We know gases conform to the shape of their container. That's the main idea of what a gas is. Gases can be characterized by their pressure. We'll also see they can be characterized by how much of the gas there is, the quantity. Usually we use the moles to indicate how much gas there is. The volume of a gas sample is important. You might remember learning about the ideal gas law and the ideal gas constant. So we'll talk about how there's gas laws that have been developed, then led us into what the ideal gas law is, how it's used, how we can use applications with the ideal gas law to solve problems, and then deal with gas mixtures. We encounter a gas mixture all the time. Air is a mixture of gases. Air is 78% N2, nitrogen, 21% O2, and about 1% everything else. And one of the main components of the 1% everything else is somewhat surprising. Does anybody know what the third most abundant component of air is? Any guesses? It turns out to be argon, which is kind of, I don't know if you would have expected argon to be the third most abundant component of air. But the 3 most abundant components of air, this is kind of an interesting sidetrack, is that those 3 components don't absorb infrared energy. They don't absorb heat in the same way that a molecule like CO2 or water vapor or methane or other gases in the atmosphere can do. So the very small component of the atmosphere that's not O2, N2, or argon acts in a much different way than those 3 molecules. And a greenhouse gas is a gas that's capable of trapping heat inside the surface of Earth, kind of like your car heats up in the summer and it's like 150 degrees inside your car, even though it's only 100 degrees outside. That's because of the greenhouse effect. Well, only certain gases can act as a greenhouse. O2, N2, not very good greenhouse gases, but they're 99% of our atmosphere. The less than 1% of our atmosphere are capable of acting as a greenhouse. Those are things that in some ways we have control over, or at least one of the molecules we do in the case of carbon dioxide. Water vapor, we don't have a whole lot of control over. Water vapor is a greenhouse gas too, but you know what happens if you put too much water vapor into air? It'll rain. It could get cloudy. That could cause cooling to take place because of cloudiness or whatever. So there already is like a natural cycle. There already is a certain amount of water vapor in air due to all the lakes and rivers and oceans that we have on Earth. So it's not like if we do a combustion reaction, we recall combustion reactions generate usually CO2 and water. It's probably the CO2 we're more worried about, because I don't know if I've ever seen it rain CO2. CO2 doesn't have a natural cycle like water has to remove itself from the atmosphere. So just a little sidetrack on something we can learn about a gas mixture and then analyze the gas mixture for some of its properties. And 99% plus of our atmosphere is really not a greenhouse gas, and it's a really small component that is. But anyways, we'll talk about gas mixtures, partial pressures, how we can know about the pressures of things like air or other mixtures. We'll talk about kinetic molecular theory of gases, effusion, diffusion, how gases escape from a pinhole. That's effusion. So effusion is like you have a hole in your tire, gas is going to escape out the pinhole. So we'll think about how different gases can escape from such a pinhole. And then diffusion is the smell of coffee permeating through your apartment in the morning. So you can think of how much time does it take the coffee smell brewing here to reach the other side of the room. That's the act of diffusion. And then we'll also talk about the end of the chapter, real gases, where they start to deviate from ideal gas behavior. A gas will really not behave like a gas anymore once it starts to liquefy. So if you can take a gas close to its condensation point, it's going to form a droplet, not be a gas anymore. So at low temperatures, we're going to see some deviations from ideal gas behavior. So this is going to be a low temperature problem. We'll also see a high pressure problem. So at high pressures, we'll see a different issue come into play. So just kind of trying to think right off the bat that real gases start to deviate from ideal gases Or another thought is gases start to behave non-ideally at primarily low temperatures or high pressures. But we'll come back to why that is towards the end of the chapter. Okay, so a few characteristics of gases to get us started. So most of the physical properties of gases are just dependent on how much gas there is. It's really not so dependent on what the actual gas particle is in terms of just the bulk properties like the pressure, the volume, et cetera. And so gases are primarily composed of our non-metallic elements, our molecular compounds, so we tend not to see metals as gases. So, of course, you know gases from very basic of science expand to fill their containers. You can compress a gas. If you had like a piston on a gas container, you can compress and increase the pressure of the container. Gases tend to have low densities. That's why they're gases. If they had high densities, they probably would have been liquefied or solidified. And if we mix gases together, they have to be what you call homogeneous. So if I take, nitrogen and oxygen, mix them together, they're going to be equally mixed. They're not going to form an oxygen layer and a nitrogen layer, so you tend not to form heterogeneous mixtures with gases. This is going to be a big consequence of gases are always in motion. So a gas sample will have particles in random motion. So if you have two gas particles in a container, they are just both in random motion, so they have to be just randomly mixed. So this is just a consequence of random motion. So the properties that we usually want to know that define characteristics of a gas sample would be the temperature of the gas, the pressure of the gas, the volume of the gas, and how much gas there is. Usually we use moles. You might recall the ideal gas law. Like at this point in the chapter, they usually don't bring up the ideal gas law yet, but you probably have seen this equation before. So why not take a look at an equation that we probably have all seen? Sometimes you see this in physics class too. Sometimes you talk about the PIV-NERT or the PV is equal to nRT equation, even in a physics class. But this is just relating the pressure times the volume of a gas is equal to nRT. So we'll talk later about what is the ideal gas constant in terms of a value in units. We'll actually show you how it was derived from some experimental data. So we'll take a look at numerically solving problems with this equation in a few moments. But for now, just think of this equation for ideal gas. What does it mean to be ideal? An ideal gas is a gas that has non-interactive particles. So if we have like O2 particles in air, they're not sticking together. They're not forming droplets is the assumption for an ideal gas. So the particles in the gas don't interact with each other. So we'll see this develop later too in the kinetic molecular theory of gases, but gas particles can collide with each other. They just bounce off each other like billiard balls, is the idea of an ideal gas. And then also they're of negligible volume, meaning that the actual volume occupied by the matter of gas is very small compared to the container volume. So if we could liquefy or solidify all the oxygen and nitrogen in this room, it would be a very small quantity. So a very small quantity of actual matter is then in the air that we're breathing in. So most of the components of a gas sample is empty space. It's just the volume container, and then a small component of that volume is the actual space being taken up by the particles of the gas. And so the ideal gas assumption is that the particles occupy just a negligible volume of their container. Now, you can imagine already why we're going to have these two break down at low temperature and high pressure. So the low temperature problem is we're going to have interactive particles. So the lower we make the temperature of a gas, and we're going to liquefy at some point. So the particle is going to start to liquefy and experience intermolecular forces. That's at a low temperature. So we have the interactive forces, and then we have the volume issue at high pressures. High pressure. Let's speak. So high pressure situations will then cause the gas to occupy a large portion of the container. So we have like a volume issue with the ideal gas law, where the particles are going to start to take up what we would say a non-negligible portion of the container, primarily at higher pressures. So we usually think of these two problems separately. At low temperatures for an ordinary gas sample at ordinary pressures, we have a problem. And then at high pressures, at ordinary temperatures, not particularly low temperatures, we have a different problem. So we'll try to look at those later as we go, but we can at least understand conceptually why the ideal gas law will break down due to those issues. take a look at pressure here. Pressure is, of the four components, it's probably the one that we don't know as well what it really means. We probably have a good idea of like hot versus cold. We have a good idea of what moles, few versus many. We can picture that. We can picture small container, big container. But what is pressure? Pressure is could be a force applied to a square area. That's the formal definition of what pressure is. So it's a force exerted onto an area. We can think about what atmospheric pressure is caused by. So the atmospheric pressure on Earth is caused by the weight of the atmosphere that's being accelerated towards Earth by gravity. And so if you could get out a balance and weigh the atmosphere, it turns out the atmospheric mass is about 5.97 times 10 to the 24 kilograms. Obviously, we didn't put that on a balance. That's approximated from whatever physicists can come up with that approximation from. So the mass of the Earth, a lot bigger than the mass of the atmosphere. Look at the mass of the atmosphere. It's like 6 orders of magnitude smaller. So the atmosphere's mass, a lot lower than Earth's mass. That probably makes sense. And so the mass of the atmosphere, about 5.15 times 10 to the 18 kilograms. Now the surface area of Earth is about 5.0 times 10 to the 14 square meters, and then gravity is about 9.8 meters per second squared. So we can actually calculate the force. Force is a mass times acceleration from physics. We don't do a whole lot of equations revolving around this, but I think it's useful to see how a pressure like atmospheric pressure is defined or derived, because you can actually take the mass of the atmosphere, use the gravitational pull as the acceleration, and then divide by the surface area of Earth. So you can use this as the atmospheric mass, use this as gravity, and then plug in the surface area of Earth, and then we should be able to calculate our average atmospheric pressure, or get an approximation of what atmospheric pressure is. And so if we take that mass 5.15 times 10 to the 18 kilograms, because it's the mass of the atmosphere that matters, not Earth. I just wanted you to see that the Earth is a lot more massive than the atmosphere. And then we multiply that by gravity. Then we're going to divide that by the surface area of Earth. Let's see what we get. I get 100,940. So that would just round to about 100,000 by sig figs. Kilograms. Now my meters goes meters to the -1, and then seconds to the -2. So it's like kilograms per meter per second squared. Not a big detail, probably not a calculation you'll ever do again, but like if you're just looking at the way the units work, that ends up with the meter to the -1, and then seconds to the -2. Now, that's what a Pascal is derived as. So the Pascal, the SI unit of pressure, which is a weird unit because we actually never commonly use. We don't commonly use Pascal, at least in chemistry class, often as the Pascal. But standard atmospheric pressure is precisely defined as 101,325 Pascal, where the Pascal is just simply the kilogram meter to the -1, second to the -2. And so the Pascal is our SI unit of pressure. And so SI units should be derived off the fundamental SI units for like mass kilogram, meter for amount, or for mass, second for time. And so this is then defined to be what we call 1 atm. Like the standard pressure unit called atmospheres is defined as 1 atm. And we usually call that standard atmospheric pressure. So standard atmospheric pressure is defined to be in Pascal, 101,325 precise Pascal. So that exact number of Pascal. So this is an exact conversion. And so that's the pressure of all the weight of the air above us being pressed down by gravity has on the surface area of Earth. Another thing that's kind of interesting, if you took a 1 meter by 1 meter, so it's about this big or so, column above Earth and go straight up into the atmosphere, that you're going to have 10 to the 4 kilograms. That's 10,000 kilograms sitting above that point. So you could think above you in the atmosphere, you have 10,000 kilograms sitting above you. Sounds like a lot. I think it is a lot, but that's all the molecules of air, everything else in the atmosphere being accelerated down towards the surface of Earth due to gravity. Okay, so I just wanted to see, like, pressure is like the force of those molecules bumping into Earth. That's where we're getting atmospheric pressure. So it's that force being exerted onto the square area of Earth. Now, if we're thinking of pressure inside of a container, you can think, well, what's the surface area of the container? We won't do the math problem for that, but think of a spherical container. What's its surface area? And then think, how much is there being pressed by gravity? So that's the pressing of the force onto the container. Think of filling up a balloon. What you're doing when you fill a balloon with more and more air before it pops is you're increasing the pressure that's being exerted on the walls of the container. Maybe it's expanding and you reach a point where the balloon breaks because the pressure went too high. So you can sort of picture that there's a force being exerted onto the surface area of that balloon. If we put too much of a force, too much mass into that balloon, it's gonna pop. Okay, let's talk about how we measure atmospheric pressure. We use a barometer in the old-fashioned way. We can just use a pressure gauge these days too, but the old style way of measuring pressure is with a barometer. We used to have those in the labs. Does anybody know if we saw barometers in the teaching labs? I don't know. If a barometer would be a big column of mercury, so you'd probably know you've seen a barometer if you've ever seen one, if you've come across one in high school or not, but they're huge columns. They have to usually be about 2 meters in length, filled with mercury, and usually there's like a dish of mercury. You can think of the atmosphere as pressing down on the mercury, just like it would any other surface of the Earth, and then you take an evacuated column, and then you dip it into the mercury, and then the mercury is going to pull up into the column to balance out the weight of the atmosphere. This is the same action as a straw. So like if you had a straw, like you're reducing the pressure when you use the straw to take a drink, and that draws the liquid up. An interesting question would be, well, what if you had a how tall would the straw have to be in order to not be able to use the straw to drink a beverage? It would have to be about 14.7 times that of mercury. A standard atmospheric pressure ends up being 760 millimeters of mercury. If you take that, and mercury is a lot more dense. Like the reason why we use mercury as a barometer is the density of mercury is about 14.7 grams per milliliter. So we're balancing out the weight of that atmosphere with mercury. Mercury is really dense, so it's not going to take as much mercury as it would a less dense material. If I used water, the column height's going to have to be 14.7 times higher because the density of water is only 1 gram per milliliter. So if we wanted to make this with water, the column height's going to have to be the standard atmospheric pressure. So the standard conversion into millimeters of mercury is 1 atmosphere is defined to be 760 precise millimeters of mercury. What that means is if we have on a given day, the actual pressure is precisely standard atmospheric pressure. It's precisely 101.325 Pascal, precisely 1.0000 atm, then the height of this column should be precisely 760 millimeters. And so 760 millimeters is not quite a, how high would 760 millimeters be? So like if you're thinking 1,000 millimeters, so it's almost a meter. And so you'd have to be 14.7 times that height if this column were made from water. And so if you're picturing a straw, and then you can reduce the pressure down to 0 at best, then you're going to need that the straw to be no taller than 14.7 times 760 millimeters. So what would that be? That'd be 11.1 meters. So if you make a straw 11.2, I don't know why you would, but if you make 11.2 meters, you'll never be able to draw the liquid up the whole way by trying to take a drink from the straw. But if you make it shorter, it would still work. So that's one of the ideas, is that you can think about how different liquids could be used in a barometer, but we use mercury because it's really has a high density. So it allows us to make a column that's as short as we can possibly make it. If we can use a even more dense material, it would be an even shorter column. So mercury is used here in the mercury barometers just to decrease the size of the barometer so it's not very tall. You can think how this could apply as well to the use of like a straw. Anyways, so the conversions here that I hope that we see is that 1 atm to Pascal, we see that conversion. There's a unit we don't use too much called the bar. This is used in meteorology. Every now and then we get our science students, meteorology students who use this unit that are in the class. So I just wanted to show that the bar unit is just dividing Pascal by 10 to the 5. So 101, 1.01325 is what the bar unit corresponds to. And then another unit is pounds per square inch, PSI. The pounds per square inch, you can think it's pounds of force being applied per square inch. So it's the same idea of force exerted onto an area. So it's 14.696 PSI per 1 atm is our standard atmospheric pressure. So we use PSI a lot in gas cylinders. We use PSI when we fill car tires. When you fill your car tire with, say, 35 PSI, I'm sure a lot of you guys have done this. If you go to the gas station and fill your gas with 35 PSI into your tire, that this is what you call a gauge pressure. So a gauge pressure is this pressure plus the standard atmospheric pressure on that given day. So like if you're filling your car tire, or let's say you go to your car tire, it's flat, and you put a pressure gauge on it, it's gonna say it's 0. That's not 0 atm total, right? That just means the tire is at atmospheric pressure. So a flat tire doesn't go to a vacuum. A flat tire is just at standard atmospheric pressure. And so if your gauge is reading 0, then it's really at atmospheric pressure in terms of your tires. And then if you put 35 PSI into your tire, you're really at about a little over two atmospheres over atmospheric pressure. So a tire filled to precisely about, say you had 14.696, let's do that times 2. So if you have a tire that's filled to about 29.3 PSI, that would be about 3 atm of total pressure in the tire. So you have the 1 atm from standard atmospheric pressure plus the 2 atm that the gauge is reading above atmospheric pressure. Now, this is just another aside, but sometimes it's useful to know this. This is also useful to know if anybody thinks back. This is probably something you guys hardly know about. Does anybody know about the Deflategate Tom Brady scandal? The football guys know this. It really wasn't much of a scandal. The scandal was that nobody knew what gauge pressure was, because there were people on TV going, oh, it's a 6-pound football, thinking like, yeah, the football weighs 6 pounds. So we're throwing like a 6-pound weight around the field. Like when you fill a football to 6 to 8 PSI, it's 6 to 8 PSI over atmospheric pressure. If you do all the calculations on were they deflating footballs, they weren't. It was just the cold temperature deflating the footballs and people not knowing how the ideal gas law works. But anyways, we'll talk a little bit about like, there's some problems in the quizzes about deflating like a balloon or a container using temperature that kind of relate back to that scandal. But anyways, gauge pressure for a tire is the PSI above atmospheric pressure. I just want to talk about a situation where you use something like a PSI. The pressure units we use in this class are mostly these units here. So these are the units we're going to use a lot in this class. At 1 atm is 760 precise millimeters of mercury. And the reason why you get millimeters of mercury is just the height of mercury in a barometer that relates back to that precise 1 atmosphere conversion. And then the torr unit, I don't know why they have 2 units that have the same conversion, but in millimeter of mercury is defined to be a torr. And so you also have 1 atm is equal to 760 torr. So the idea would be that 745 millimeters of mercury would just be equal to 745. So kind of silly that we have 2 units, but you'll see those 2 units used a lot in chapter 10. And then also you'll see conversions to and from atm a lot. You'll have these conversions given to you, so you don't have to memorize them, but these are the ones that we'll use a lot in this chapter. So let's convert that pressure of 745.0 torr into some other units. So obviously to millimeters of mercury, that's the really easy one. They're the same unit. So this would just be 745.0 millimeters of mercury. So they are the same unit as each other. I can go either torr or millimeters of mercury in this step to show their conversion into ATM. So the number of ATM in 745 torr, this is really easy. This is just a 760 torr is 1 ATM. So this should just be a little bit less than 1 atmosphere. Now let's talk sig figs real quick. This period, this is trying to mean that this is an exact conversion. Like that's precisely how many torr there are in an ATM. I'm not rounding to 2 sig figs. So I'm keeping all 4 that I start with here. So I have 4 sig figs in my value. I'm gonna keep 4, so I get 0.9803 ATM, or atmospheres. So a little bit less than the pressure of standard atmospheric pressure at 745.0 torr. Now, daily atmospheric pressure will range, I don't know what the precise values are, but it'll range from a little bit below 760 to a little bit above 760, probably plus or minus 40 or 50 torr on a given day. It has to do with high pressure versus low pressure days. You can relate that to meteorology reports you might sometimes see. But the number of Pascal in this measurement, if we start with we can start with the torr or the ATM number that we have. But let's just go from torr and show that one way we might write this out is that 760 torr is 1 ATM, and then 1 ATM into Pascal is just that conversion, 101.325 Pascal. And so this should be a little bit less than 101.325. So I get 99,330 to 4 sig figs. And again, this is an exact conversion too. So if we had, sig figs always annoys the conversation, but if we had, 7 placeholders in our torr value, we'd keep all 7 because the 101.325 is an exact conversion. And then lastly, the PSI here within this example would be 745.0 torr, 760 torr is 1 ATM, 1 ATM, 14.696 pounds per square inch. This would be our total PSI. This is kind of gets off the whole point of the conversion here, but if we're reading this on a gauge, this is a different question than just the total PSI. So think of this question asking, what's the total PSI of this conversion? Is just doing this simple conversion here. It'd be 14.4. Need one more sig fig, 14.41 PSI. Not to get too complicated with the tire example, but this would be the pressure above atmospheric pressure. If you read this on a gauge, you would say, well, 14.4 PSI is about 745 torr above standard atmospheric pressure. Okay, keyword is Gibbs for today. But that'll do us for today, and I'll see you guys back here on Friday.